Well, welcome back to our course, Computer Organization and Architecture. For this lecture, we're going to be talking about parallel processing, and this is going to be the last section. And so now we're going to be talking about parallel organization over a couple of lectures. And like I said, we're going to be starting for this one, focusing on parallel processing. So, as we typically do, let's go ahead and give a little introduction to the things that we're going to discuss. We'll get into it and then we'll come back to the same page and reflect on what we have talked about. So, we'll be talking about multiprocessor organization, types of parallel processing system, parallel organizations. We'll talk about symmetric multiprocessors. We'll talk about cache coherence and the MESI protocol. Then we'll get into multi-threading and chip multiprocessors. We'll talk about clusters, and then we'll finish up with non-uniform memory access. So here we're talking about the multiple processor organization, the taxonomy. So a taxonomy that was first introduced by Flynn is still the most common way of categorizing systems with parallel processor capability. Flynn proposed the following categories of computer systems. First, there's a single instruction, single data, SISD stream. A single processor executes a single instruction stream to operate on data stored in a single memory. Uniprocessors fall into this category. Next, we have SIMD, the single instruction, multiple data. And so for this stream, a single machine instruction controls the simultaneous execution of a number of processing elements on a lockstep basis. Each processing element that has an associated data memory so that instructions are executed on different set of data by different processors. Vector and array processors fall into this category and are discussed in section 18.7. So keep that in mind. We have MISD, multiple instructions, single data streams. And so for these, it's a sequence of data is transferred to a set of processors, each of which executes a different instruction sequence. This structure is not commercially implemented. Finally, we have multiple instruction, multiple data, MIMD. And so there's a stream for this, and a set of processors simultaneously executes different instruction sequences on different data sets. SMPs, clusters, and NUMA systems fit into this category. So here's another way of looking at it in a figure. So with the MIMD organization, the processors are general purpose. Each is able to process all the instructions necessary to perform the appropriate data transformations. MIMDs can be further subdivided by the means in which the processors communicate. And this is what we're showing here in figure 20.1. If the processors share a common memory, then each processor accesses programs and data stored in the shared memory, and processors communicate with each other via that memory. The most common form of such system is known as symmetric processors, symmetric multiprocessors, SMP, which we will examine in section 20.2. In a SMP, multiple processors share a single memory or pool of memory by means of a shared bus or other interconnection mechanisms. A distinguishing feature is that the memory access time to any region of memory is approximately the same for each processor. A more recent development is the non-uniform memory access, NUMA, organization, which is described in section 20.6. As the name suggests, the memory access time to different regions of memory may differ for a NUMA processor. A collection of independent uniprocessors, or SMPs, may be interconnected to form a cluster. Communication among the computers is either via fixed paths or some network facility. So here in figure 20.2, it illustrates the general organization of the taxonomy of figure 20.1. Figure 20.2a shows the structure of an SISD. There is some sort of control unit, CU, that provides an instruction stream, IS, to a processing unit, PU. The processing unit operates on a single data stream, DS, from a memory unit, MU. Within SIMD, there is still a single control unit, now feeding a single instruction stream to multiple PUs. Each PU may have its own dedicated memory. This is illustrated in figure 20.2b, or there may be a shared memory. Finally, with MIMD, there are multiple control units, each feeding a separate instruction stream to its own PU. The MIMD may be a shared memory multiprocessor, which is shown in figure 20.2c, or a distributed memory multi-computer, which is shown in figure 20.2d. The design issues related to SMPs, clusters, and NUMAs are complex, involving issues relating to physical organization, interconnection structures, interprocessor communication, operating system design, and application software techniques. Our concern here is primarily with organization, although we touch briefly on operating system design issues. Until fairly recently, virtually all single-user personal computers and most workstations contain a single general-purpose microprocessor. As demands for performance increase, and as the cost of microprocessors continue to drop, vendors have introduced systems with an SMP organization. The term SMP refers to a computer hardware architecture and also to the operating system behavior that reflects that architecture. An SMP can be defined as a standalone computer system with the following characteristics. One, there are two or more similar processors of comparable capability. Two, the processors share the same main memory and I/O facilities and are interconnected by a bus or other internal connection scheme such that the memory access time is approximately the same for each processor. Three, all processors share access to I/O devices either through the same channels or through different channels that provide paths to the same device. Four, all processors can perform the same function, hence the term symmetric. Five, the system is controlled by an integrated operating system that provides interaction between processors and their programs at the job, task, file, and data element levels. Point 1 to 4 should be self-explanatory. Point 5 illustrates one of the contrast with a loosely coupled multiprocessor system, such as a cluster. In the latter, the physical unit of interaction is usually a message or complete file. In an SMP, individual data elements can constitute the level of interaction, and there can be a high degree of cooperation between processors. The operating system of an SMP schedules processes or threads across all of the processors. An SMP organization has a number of potential advantages over a uniprocessor organization, including the following. First, there's performance. If the work can be done by a computer, can be organized so that some portions of the work can be done in parallel, then a system with multiprocessors will yield greater performance than one with a single processor of the same type. We're showing this in figure 20.3. Next, there's availability. In a symmetric multiprocessor, because all processors can perform the same function, the failure of a single processor does not halt the machine. Instead, the system can continue to function at reduced performance. Then we have incremental growth. A user can enhance the performance of a system by adding an additional processor. Plus, we have scaling. Vendors can offer a range of products with different price and performance characteristics based on a number of processors configured in the system. It's important to note that these are potential rather than guaranteed benefits. The operating system must provide tools and functions to exploit the parallelisms in an SMP system. An attractive feature of the SMP is the existence of multiple processors and is transparent to the user. The operating system takes care of scheduling of threads or processes on individual processors and of synchronizing among processors. Figure 20.4 depicts in general terms the organization of a multiprocessor system. There are two or more processors. Each processor is self-contained, including a control unit, ALU, registers, and typically one or more levels of cache. Each processor has access to a shared main memory and the I/O devices through some form of interconnection mechanism. The processors can communicate with each other through memory, say for messages and status information left in common data areas. It may also be possible for processors to exchange signals directly. The memory is often organized so that multiple simultaneous accesses to separate blocks of memory are possible. In some configurations, each processor may also have its own private main memory and I/O channels in addition to the shared resource. The most common organization for personal computers, workstations, and servers is a time-shared bus. The time-shared bus is the simplest mechanism for constructing a multiprocessor system, and we're showing this in figure 20.5. The structure and interfaces are basically the same as for a single processor system that uses a bus interconnection. The bus consists of a controller, an address, and data lines. So control, address, and data lines. To facilitate DMA transfers from I/O subsystem to processor, the following features are provided. First, there's addressing. It must be possible to distinguish modules on the bus to determine the source and destination of data. Next, there needs to be arbitration. Any I/O module can temporarily function as quote, master. A mechanism is provided to arbitrate competing requests for bus control using some sort of priority scheme. And then finally, time sharing. When one module is controlling the bus, other modules are locked out and must, if necessary, suspend operation until bus access is achieved. These uniprocessor features are directly usable in an SMP organization. In this latter case, there are now multiple processors as well as multiple I/O processors, all attempting to gain access to one or more memory module via the bus. The bus organization has several attractive features. First, there's simplicity. There is the simplicity. It is the simplest approach to multi-processor organization. The physical interface and the addressing and arbitration and time sharing logic of each processor remains the same as in a single processor system. Second, there's flexibility. It is generally easy to expand the system by attaching more processors to the bus. And finally, reliability. The bus is essentially a passive medium, and the failure of any attached device should not cause failure of the whole system. It's a nice feature. In terms of the disadvantages, the major drawbacks to the bus organization is performance. All memory references pass through the common bus. Thus, the bus cycle time limits the speed of the system. To improve performance, it is desirable to equip each processor with a cache memory. This should reduce the number of bus accesses dramatically. Typically, workstation and PC SMPs have two levels of cache, with the L1 cache internal. It's the same chip as the processor, and the L2 cache either internal or external. Some processors now employ L3 cache as well. The use of caches introduced some design considerations. Because each local cache contains an image of a portion of memory, if a word is altered in one cache, it could conceivably invalidate a word in another cache. To prevent this, the other processors must be alerted that an update has taken place. This problem is known as cache coherence problem and is typically addressed in the hardware rather than the operating system. An SMP operating system manages processors and other computer resources so that the user perceives a single operating system controlling system resources. In fact, such a configuration should appear as a single processor multi-programming system. Both the SMP and uniprocessor cases, multiple jobs or processes may be achieved at one time. It is the responsibility of the operating system to schedule their execution and to allocate resources. A user may construct applications that use multiple processors or multiple threads within processes without regards to whether a single processor or multiprocessors will be available. Thus, a multiprocessor operating system must provide all the functionality of a multi-programming system plus additional features to accommodate multiple processors. Among the key design issues are, number one, simultaneous concurrent processes. The operating system routes need to be re-entrant to allow several processors to execute the same IS code simultaneously, with multiple processors executing the same or different parts of the OS. OS tables and management structures must be managed properly to avoid deadlock or invalid operations. Next, there's scheduling. Any processor may perform scheduling to conflict, so conflicts must be avoided. The scheduler must assign ready processes to available processors. Then we have synchronization, multiple active processes having potential access to shared address spaces or shared I/O resources. Care must be taken to provide effective synchronization. Synchronization is a facility that enforces multiple exclusion and event ordering. Then we have memory management. The memory management on a multiprocessor must deal with all of the issues found on a uniprocessor machine, as discussed in Chapter 9. In addition, the operating system needs to exploit the available hardware parallelisms, such as multi-ported memories, to achieve the best performance. The paging mechanism on different processors must be coordinated to enforce consistency when several processors share a page or segment and to decide on page replacement. And finally, we have reliability and fault tolerance. The operating system should provide graceful degradation in the face of processor failures. The scheduler and other portions of the operating system must recognize the loss of a processor and reconstruct management tables accordingly. So in terms of cache coherence, software cache coherence schemes attempt to avoid the need for additional hardware circuitry and logic by relying on the compiler and operating system to deal with a problem. Software approaches are attractive because the overhead of detecting potential problems is transferred from runtime to compile time, and the design complexity is transferred from hardware to software. On the other hand, compile times software approaches generally must make conservative decisions leading to inefficient cache utilization. Compiler-based coherence mechanisms perform an analysis on the code to determine which data items may become unsafe for caching and then mark those items accordingly. The operating system or hardware then prevents non-cacheable items from being cached. The simplest approach is to prevent any shared data variables from being cached. This is too conservative because a shared data structure may be exclusively used during some periods and may be effectively read-only during either period. It is only during periods when at least one process may update the variables and at least one other process may access the variables that cache incoherence is an issue. More efficient approaches analyze the code to determine the safe periods for shared variables. The compiler then inserts instructions into the generated code to enforce cache coherence, during the critical periods. A number of techniques have been developed for performing the analysis and for enforcing the results. So there's some references in the text if you wanted to pursue that further. Following on, hardware-based solutions are generally referred to as cache coherence protocols. These solutions provide dynamic recognition of at runtime of potential inconsistency conditions. Because the problem is only dealt with when it actually arises, there is more effective use of caches, leading to improved performance over a software approach. In addition, these approaches are transparent to the programmer and the compiler, reducing the software development burden. Hardware schemes differ in a number of particulars, including where the state information about data lines is held, how the information is organized, where coherence is enforced, and the enforcement mechanisms. In general, hardware schemes can be divided into two categories: directory protocols and Snoopy protocols. Directory protocols collect and maintain information about where copies of lines reside. Typically, there is a centralized controller that is part of the main memory controller and a directory that is stored in main memory. The directory contains global state information about the contents of the various local caches. When an individual cache controller makes a request, the centralized controller checks and issues necessary commands for data transfer between memory and caches or between caches. It is also responsible for keeping the state information up to date. Therefore, every local action that can affect the global state of the line must be reported to the central controller. Typically, the controller maintains information about which processors have a copy of which lines. Before a processor can write to a local copy of a line, it must request exclusive access to the line from the controller. Before granting this exclusive access, the controller sends a message to all processors with a cache copy of the line, forcing each processor to invalidate its copy. After receiving acknowledgement back from each such processor, the controller grants exclusive access to the requesting processor. When another processor tries to read a line that is exclusively granted to another processor, it will send a missed notification to the controller. The controller then issues a command to the processor holding that line that requires the processors to do a write back to main memory. The line may now be shared for the reading by the original processor and the requesting processor. Directory schemes suffer from a drawback of a central bottleneck and the overhead of communicating between the various cache controllers and the central controller. However, they are effective in large-scale systems that involve multiple buses or some other complex interconnection schemes. So next, talk about Snoopy protocols. In case you're a Peanuts fan, you'll maybe have thought about this, or at least the name. Snoopy protocols distribute the responsibility for maintaining cache coherence among all the cache controllers in a multiprocessor. A cache must recognize that a line that it holds is shared with other caches. When an update action is performed on a shared cache line, must be announced to all the other caches by a broadcast mechanism. Each cache controller is able to, quote, snoop on the network to observe these broadcasted notifications and react accordingly. Snoopy protocols are ideally suited to bus-based multiprocessors because the shared bus provides a simple means for broadcasting and snooping. However, because one of the objectives of the use of local cache is to avoid bus accesses, care must be taken that the increased bus traffic required for broadcasting and snooping does not cancel out the gains from the use of local cache. Two basic approaches to the SNP protocol have been explored: write and validate and write update, or you could call it write broadcast. With a write invalidate protocol, there can be multiple readers, but only one writer at a time. Initially, a line may be shared among several caches for reading purposes. When one of the caches wants to perform a write to the line, it first issues a notice that invalidates that line in the other caches, making the line exclusive to their writing cache. Once a line is exclusive, the owning processor can make cheap local writes until some other processor requires the same line. The write and validate approach is the most widely used in commercial multiprocessor systems, such as the x86 architecture. It marks the state of every cache line using 2 extra bits in the cache tag as modified, exclusive, shared, or invalid. For this reason, the write and invalidate protocol is called messy. In the remainder of this section, we will look at its use among local caches across multiprocessors. For simplicity in what we're discussing here, we will not examine the mechanisms involved in coordinating among both level 1 and level 2 locally, as well as at the same time coordinating across the distributed multiprocessor. This would not add any new principles, but would greatly complicate the discussion. So let's talk about write update. So with a write update protocol, there can be multiple writers as well as multiple readers. When a processor wishes to update a shared line, the word to be updated is distributed to all others, and caches containing that line can update it. Neither of these two approaches is superior to the other under all circumstances. Performance depends on the number of local caches and the pattern of memory reads and writes. Some systems implement adaptive protocols that employ both write invalidate and write update mechanisms. To provide cache consistency on an SMP, the data cache often supports a protocol known as messy. For messy, the data cache includes 2 status bits per tag so that each line can be modified, be one of 4 states. So here's the messy, MESI, so modified, exclusive, shared, and invalid. So for modified, the line in the cache has been modified. That is, it's different from the main memory and is available only in this cache. There's exclusive. The line in the cache is the same as that in the main memory and is not present in any other cache. Shared, the line in the cache is the same as that in the main memory and may be present in another cache. Finally, invalid, the line in the cache does not contain invalid data. So here we're showing in table 20.1, it summarized the meaning of these 4 states. And so we've already gone over this, but if you want a nice summary, you can just pause the video and look over that in more detail. Figure 20.6 displays a state diagram for the messy protocol. Keep in mind that each line of the cache has its own state bits and therefore its own realization of the state diagram. Figure 20.6a shows the transitions that occur due to actions initiated by the processor attached to this cache. Figure 20.6b shows the transitions that occur due to events that are snooped on the common bus. So with what we're showing here, we're getting a chance to see the separate state diagrams for processor initiated and bus initiated actions, which helps clarify the logic of the messy protocol. At any time, a cache line is in a single state. If the next event is from the attached processor, then the transition is dictated by figure 20.6a, and if the next event is from the bus, the transition is dictated by figure 20.6b. Here in figure 20.7, we summarize the state relationships between lines and different caches, all of which map to the same block of memory. So once again, you can pause the video if you want and look at this a little bit longer, but I'm going to go ahead and move on. So when a read miss occurs in the local cache, the processor initiates a memory read to read the line of the main memory containing the missing address. The processor inserts a signal on the bus that alerts all the other processor/cache units to snoop the transaction. There are a number of possible outcomes. One, if one other cache has a clean that is unmodified since the read from memory copy the line in the exclusive state, it returns a signal indicating that it shares this line. The responding processor then transitions the state of its copy from exclusive to shared, and the initiating processor reads the line from main memory and transitions the line in the cache from invalid to shared. If one or more caches have a clean copy of the line in the shared state, each of them signals that it shares a line. The initiating processor reads the line and transitions its line in the cache from invalid to shared. If one other cache has modified a copy of the line, then the cache blocks the memory read and provides the line to the requesting cache over the shared bus. The responding cache then changes its line from modified to shared. The line sent to the requesting cache is also received and processed by the memory controller, which stores the block in memory. If no other cache has a copy of the line, that is, it's clean or modified, then no signals are returned. The initiating processor reads the line and transitions the line in its cache from invalid to exclusive. When a read hit occurs on a line currently in the local cache, the processor simply reads the required item. There's no state change. The state remains modified, shared, or exclusive. So for write miss, when a write miss occurs in the local cache, the processor initiates a memory read to read the line of the main memory containing the missing address. For this purpose, the processor issues a signal on the bus that means read with intent to modify. When the line is loaded, it is immediately marked modified with respect to other caches. Two possible scenarios precede the loading of the line of data. First, some other cache may have a modified copy of this line, that is, the state is equal to modified. In this case, the alerted processor signals the initiating processor that another processor has a modified copy of the line. The initiating processor surrenders the bus and waits. The other processor gains access to the bus, writes the modified cache line back to the main memory, and transitions the state of the cache line to invalid. That is because the initiating processor is going to modify this line. Subsequently, the initiating processor will again issue a signal to the bus and then read the line from the main memory. So this is it sends this RWITM, read with intent to modify. Then read the line from the main memory, modify the line in the cache, and mark the line in the modified state. The second scenario is that no other cache has a modified copy of the requested line. In this case, no signal is returned, and the initiating processor proceeds to read in the line and modify it. Meanwhile, if one or more caches have a clean copy of the line in the shared state, each cache invalidates its copy of the line, and in one cache has a clean copy of the line. In the exclusive state, it invalidates the copy of the line. So we talked about the write miss, and then we have the write hit. And so a write hit occurs on a line. Currently in the local cache, the effect depends on the current state of the line in the local cache. If it's shared before performing the state, the processor must gain exclusive ownership of the line. The processor signals intent on the bus. Each processor then has a shared copy of the line in its cache. transitions the sector from shared to invalid. The initiating processor then performs the update and transitions its copy of the line from shared to modified. If it's an exclusive, the processor already has the exclusive control of the line, and so it simply performs the update and transitions its copy of the line from exclusive to modified. Finally, for modified, the processor already has exclusive control of this line and has the line marked as modified, and so simply performs the update. Okay, well, here we have a couple figures. First, in figure 20.8, where you show the initiator read from a write-back cache. So it will help to clarify the state transition diagram of 20.6 to develop flowcharts that show the exchange of signals between cooperating cache during a read or write operation. The following flowchart assumes an initiator system and one or more other participants and refer to the state of the cache line in each system that all map to the same block of main memory. Figure 20.8 covers the case of a memory read operation. If the desired word is contained in a cache line of the initiator's cache, then the line must be in the M, E, or S states. In that case, the word is retrieved from the cache and returned to the processor. If the cache line is not present, then the initiator signals a read miss to the other participants. This indicates that it is going to perform a read memory operation to bring in the memory block containing the desired word after waiting for responding signals. Then, if necessary, the initiator writes back a line of cache to the main room for the incoming block. If the participant and the participant checks to see if the requested block is in a line of its cache. If not, it signals back null and is done. If the participant has the desired line in either the E or S state, it signals S because now the line will be shared with the initiator and sets the line state to S. If the line is in the M state, it signals M to the initiator. Then the participants write back the line to bring main memory up to date and move to an S state. If an initiator receives a signal M, it waits until the participant has written the line back to memory before proceeding. If the signal is M or S, the initiator sets the line to S, and if the incoming signal is null, it sets the state to E. Once again, the state is set, the target line is located. So figure 20.8 indicates the interaction between an initiator and a single participant. If there are multiple other cache systems, the initiator needs to take into account all incoming signals. If an M signal is received and other signals received should be S or null, the initiator responds to the M signal by waiting for the WB signal. If there is no M signal but one or more S signals, then the initiator responds to that. Here in figure 20.9, we're showing the initiator write back cache, and it is a flowchart showing that when the initiator performs a write to the write back cache, if the block containing the word to be written is already in a line of the cache, that is, it's a hit, the initiator updates the line to the cache and sets the line state to M. It also signals a write hit to participants who set that line to invalid. If the desired line is not in the cache, the initiator signals a write miss to the other participants. The rest of the flowchart is similar to what we were showing in figure 20.8. So let's talk about multi-threading and chip multiprocessors. The most important measure of performance for a processor is the rate at which it executes instructions. This can be expressed as MIPS, and the MIPS rate is F times IPC, where F is the processor clock frequency in megahertz, and IPC is the average instructions per cycle. So Accordingly, designers have pursued the goal of increasing performance on two fronts: increasing clock frequency and increasing the number of instructions executed on, or executed, or more properly, the number of instructions that complete during a processor cycle. As we have seen in earlier chapters, designers have increased IPC by using instruction pipelines and then by using multiple parallel instruction pipelines in a superscalar architecture. With pipelined and multi-pipeline designs, the principal problem is to maximize the utilization of each pipeline stage. To improve throughput, designers have created even more complex mechanisms, such as executing some instructions in a different order from the way that they occurred in the instruction stream, and beginning execution of instructions that may never be needed. And we've already talked about this, sort of some counterintuitive things that actually can and do improve performance. But as was discussed in section 2.2, this approach may be reaching a limit due to the complexity and power consumption concerns. An alternative approach, which allows for high degree of instruction level parallelisms without increasing circuit complexity or power consumption, is called multi-threading. And in essence, the instruction stream is divided into several smaller streams known as threads, such that the threads can be executed in parallel. The variety of specific multi-threading designs realized in both commercial systems and experimental systems is vast. And so in this section, we will give a brief survey of the major concepts. So the concept of thread used in discussing multi-thread processors may or may not be the same as the concept of software threads in a multi-program operating system. It will be useful to define terms here briefly. First of all, for a process, this is an instance of a program running on a computer. A process embodies two key characteristics. First, resource ownership. A process includes a virtual address space to hold a process image. The process image is the collection of programs, data, stack, and attributes that define the process. From time to time, a process may be allocated control or ownership of resources such as main memory, I/O channels, I/O devices, and files. Second, there's scheduling and / execution. The execution of a process follows an execution path, that is a trace, through one or more programs. This execution may be interleaved with that of other processes. Thus, a process has an execution state, such as running, ready, etc., and a dispatching priority with and its entities that is scheduled and dispatched by the operating systems. Okay, let's talk about a few other things. We have a processor switch, an operation that switches the processor from one process to another by saving all the process control data registers and other information for the first and replacing them with the process information for the second. We have threads. So this is a dispatchable unit of work within a process. It includes a processor content, which includes the program counter and stack pointer, and its own data for the stack to enable subroutine branching. A thread executes sequentially and is interruptible so that the processor can turn to another thread. There's a switch thread. The act of switching processor control from one thread to another within the same process. Typically, this type of switch is much less costly than a process switch. Thus, a thread is concerned with scheduling and execution, whereas a process is concerned with both scheduling / execution and resource ownership. The multiple threads within a process share the same resource. This is why a thread switch is much less time-consuming than a process switch. Traditional operating systems, such as earlier versions of Unix, did not support threads. Most modern operating systems, such as Linux, other versions of Unix, and Windows do support threads. A distinction is made between a user-level threads, which are visible to the application program, and kernel-level threads, which are visible only to the operating system. Both of these may be referred to as an explicit thread that is defined in software. All of the commercial processors and most of the experimental processors so far have used explicit multithreading. These systems concurrently execute instructions from different explicit threads, either by interleaving instructions from different threads or shared pipelines, or by parallel execution on parallel pipelines. Implicit multithreading refers to the concurrent execution of multiple threads extracted from a single sequence program. These implicit threads may be defined either statically or by the compiler or dynamically by the hardware. So in the remainder of what we're going to talk in this section, we will consider explicit multithreading. So broadly speaking, there are four principal approaches to multithreading. We have interleave multithreading. This is also known as fine-grained multithreading. The processor deals with two or more threads contexts at a time, switching from one thread to another at each clock cycle. The thread is blocked because of data dependencies or memory latencies. That thread is skipped and a ready thread is executed. Next, we have blocked multithreading. And so this is also known as a coarse-grained multithreading. The instructions of a thread are executed successfully until the events occurs that may cause delays, such as a cache miss. This event induces a switch to another thread. This approach is effective on an in-order process that would stall the pipeline for a delay event, such as a cache miss. Then we have simultaneous multithreads, SMT. Instructions are simultaneously issued from multiple threads to the execution unit of a superscalar processor. This combines a wide superscalar instruction issue capacity with the use of a multiple thread context. And finally, we have chip multiprocessing. In this case, the entire processor is replicated on a single chip, and each processor handles separate threads. The advantage of this approach is that the available logic area on a chip is used effectively without depending on ever-increasing complexity in the pipeline design. For the first two approaches, instructions from different threads are now executed simultaneously. Instead, the processor is able to rapidly switch from one thread to another using a different set of registers and other context information. This results in a better utilization of the processor's execution resources and allows a large penalty and avoids a large penalty due to cache misses and other latency events. The SMT approach involves true simultaneous execution of instructions from different threads using replicated execution resources. Chip multiprocessing also enables simultaneous execution of instructions from different threads. Figure 20.10, which we're showing here, illustrates some of the possible pipelining architectures that involve multithreading and contrasts these with approaches that do not use multithreading. Each horizontal row represents the potential issue slot or slots for a single execution cycle. That is, the width of each row corresponds to the maximum number of instructions that can be issued in a single clock cycle. The vertical dimension represents the time sequence of clock cycles. An empty, that is shaded slot, represents an unused execution slot in one pipeline. A no-op is indicated by an N. So the first three illustrations in figure 20.10 show different approaches with a scalar that is a single issue processor. We have the single threaded scalar. This is a simple pipeline found in traditional RISC and CISC machines with no multithreading. We have interleaved multithreading scalar. This is the easiest multithreading approach to implement. By switching from one thread to another at each clock cycle, the pipeline stages can be kept fully occupied or close to fully occupied. The hardware must be capable of switching from one thread context to another between cycles. Then we have block multi-threading scaler. In this case, a single thread is executed until a latency event occurs that would stop the pipeline, at which time the processor switched to another thread. Figure 20.10c shows a situation which the time to perform a thread switch is one cycle, whereas 20.10b shows that thread switching occurring in 0 cycles. In the case of interleaved multi-threading, it is assumed that there are no control or data dependencies between threads, which simplifies the pipeline design and therefore should allow a thread switch with no delay. However, depending on the specific design and implementation, block multi-threading may require a clock cycle to perform a thread switch, as illustrated in 20.10, which we're showing. This is true if a fetch instruction triggers the thread switch and must be discarded from the pipeline. Although interleaved multi-threading appears to offer better processor utilization than block multi-threading, it does so at the sacrifice of single thread performance. The multiple threads compete for cache resources, which raises the probability of a cache miss for a given thread. More opportunities for parallel execution are available if a processor can issue multiple instructions per cycle. Figure 20.10d through 20.10i, so hopefully you can scan through this whole table here to see all of these, illustrate a number of variations among processors that have hardware for issuing 4 instructions per cycle. In all these cases, only instructions from a single thread are issued in a single cycle. The following alternatives are illustrated. So superscalar, this is a basic superscalar approach with no multi-threading. Until relatively easy, this was the most powerful approach to providing parallelisms within a processor. Note that during some clock cycles, not all of the available issue slots are used. During this cycle, less than the maximum number of instructions is issued. This is referred to as horizontal loss. During other instruction cycles, no issue slots are used. These are cycles when no instructions can be issued. This is referred to as vertical loss. Interleaved multi-threading superscalar. During each cycle, as many instructions as possible are issued from a single thread. With this technique, potential delay due to threads switches are eliminated as previously discussed. However, the number of instructions issued on any given cycle is still limited by dependencies that exist within any given thread. We have blocked multi-thread superscalar. So again, instructions from only one thread may be issued during any cycle, and blocked multi-threading is used. We also have very long instruction word, VLIW. A VLIW architecture such as IA64 places multiple instructions in a single word. Typically, a VLIW is constructed by the compiler, which places operations that may be executed in parallel in the same word. In a simple VLIW machine, figure 20.10G, and so you can see that here, we're showing that, it is not possible to completely fill the word with instructions to be issued in parallel. Thus, in that case, no ops are used, and those are the ones showing the N, if you don't recall me saying that. So we have interleaved multi-threading. This approach should provide similar efficiencies to those provided by interleaved multi-threading on the superscalar architecture. We have block multi-threading, VLIW. This approach should provide similar efficiencies to those provided by block multi-threading on a superscalar architecture. The final two approaches illustrated in figure 1020 enable the parallel simultaneous execution of multi-threads. We have multitaneous multi-threading. Figure 2010I shows a system capable of 8 instructions at a time. If one thread has a high degree of instruction level parallelism, it may on some cycles be able to fill all the horizontal slots. On on other cycles, instructions from 2 or more threads may be issued. If sufficient threads are active, it should usually be possible to issue the maximum number of instructions on each cycle, providing a high level of efficiency. We have chip multiprocessor multi-core. 20.10K shows a chip containing 4 cores, each of which has two issue superscalar processor. Each core is assigned a thread from which it can issue up to 2 instructions per cycle. We discuss multi-core computers in chapter 21, so we'll save that for our next lecture. Comparing figure 2010I and 2010K, we see a chip multiprocessor with the same instruction issue capacity as the SMT can achieve the same degree of instruction parallelism. This is because the chip multiprocessor is not able to hide latencies by issuing instructions from other threads. On the other hand, the chip multiprocessor should outperform a superscalar processor with the same instruction issue capability because the horizontal losses will be greater for the superscalar processor. In addition, it is possible to use multi-threads within each of the cores on a chip multiprocessor, and this is done by some contemporary machines. Okay, well that's a mouthful, but you can once again see this is another point in terms of computer architecture and organization where there are a lot of possible things that we've allowed ourselves to be able to trade between in thinking of what is best for a specific application. And we're trying to give an overview of that as we're going through this chapter. So next, let's talk about clusters. An important and relatively recent development in computer system design is clustering. Clustering is an alternative to symmetric multiprocessing as an approach to providing high performance and high availability, and is particularly attractive for server applications. We can define a cluster as a group of interconnected whole computers working together as a unified computing resource that can create the illusion of being one machine. The term whole computer means a system that can run on its own apart from the cluster. In the literature, each computer in a cluster is typically referred to as a node. So, reference from the textbook, it mentions there are 4 benefits that can be achieved with clustering. These can also be thought of as objectives or design requirements. And so we're going to just go ahead and list those things here. So first of all, there's absolute scalability. It is possible to create large clusters that are far surpass the power of even the largest standalone machines. A cluster can have tens, hundreds, or even thousands of machines, each of which is a multiprocessor. You can have incremental scalability. A cluster is configured in such a way that it is possible to add new systems to the cluster in small increments. Thus, a system can start out with a modest system and expand it as needed as needs grow without having to go through a major upgrade in which an existing small system is replaced with a larger system. High availability, because each node is a cluster, and a cluster is a standalone computer, the failure of one node does not mean loss of service. In many products, fault tolerance is handled automatically in software. Finally, we have superior price/performance. By using commodity building blocks, it is possible to put together a cluster with equal or greater computing power than a single large machine at much lower cost. In the literature, clusters are classified in a number of different ways. Perhaps the simplest classification is based on whether the computer is a cluster shared access to the same disks. Figure 2011A, which we're showing, shows a 2-node cluster in which the only interconnection is by means of a high-speed link that can be used for messaging exchange to coordinate cluster activity. The link can be a LAN, a local area network, that is shared with other computers that are not part of the cluster, or the link can be a dedicated interconnection facility. In the latter case, one or more of the computers in the cluster will have a link to the local area network, LAN, or WAN, wide area network, so that there is a connection between the server clusters and the remote client systems. Note that in the figure, each computer is depicted as being a multiprocessor. This is not necessary, but does enhance both performance and availability. In this simple classification depicted in figure 2011, the other alternative is a shared disk cluster. In this case, there generally is still a message link between nodes. In addition, there is a disk subsystem that is directly linked to multiple computers within the cluster. In this figure, the common disk subsystem is a RAID. We talked about RAID systems before. The use of RAID or some similar redundancy disk technology is common in clusters, so that the high availability achieved by the presence of multiple computers is not compromised by a shared disk that is a single point of failure. The common older method known as passive standby is simply to have one computer handle all of the processing load while the other computer remains inactive, standing by to take over in the event of a failure of the primary. To coordinate the machines, the active or primary machine periodically sends a heartbeat message to the standby machine. Should these messages stop arriving, the standby assumes that the primary server has failed and puts itself into operation. This approach increases availability but does not improve performance. Further, if the only information that is exchanged between the two systems is a heartbeat message, and if two systems do not share common disks, then the standby provides a functional backup, but has no access to the databases managed by the primary. The passive standby is generally not referred to as a cluster. The term cluster is reserved for multiple interconnecting computers that are all actively doing processing while maintaining the image of a single system to the outside world. The term active secondary is often used to refer to the configuration. Three classifications of clustering can be identified: separate server, shared nothing, and shared memory. In one approach to clustering, each computer is a separate server with its own disk, and there are no disks shared between the systems. We're showing that in figure 2011A. This arrangement provides high performance as well as high availability. In this case, some type of management or scheduling software is needed to assign incoming client requests to servers so that the load is balanced and high utilization is achieved. It is desirable to have a fallout capability, which means that if a computer fails while executing an application, another computer in the cluster can pick up and complete the application. For this to happen, data must constantly be copied among systems so that each system has access to the current data of the other systems. The overhead of this data exchange ensures high availability at a cost of performance penalty. To reduce the communication overhead, most clusters now consist of servers connected to common disk. And so that's shown in figure 2011B, and we can see those common disks here in that RAID environment. In one such variation on this approach called shared nothing, the common disks are partitions into volumes, and each volume is owned by a single computer. If that computer fails, the cluster must be reconfigured so that some other computer has ownership of the volumes of the failed computers. It is also possible to have multiple computers share the same disk at the same time, which is called a shared disk approach, so that each computer has access to all of the volumes on all of the disks. The approach requires the use of some type of locking facility to ensure that the data can only be accessed by one computer at a time. So a clearer picture of the range of cluster options can be gained by looking at the functional alternatives. And so table 20.2 provides a useful classification among functional lines. And so you might want to just reflect on this. You can pause the video. We've already talked about this, but this is a nice summary way to review what we've gone over. In terms of commercial products, the two common approaches to providing a multiprocessor system to support applications are SMP and clusters. For some years, another approach known as non-uniform memory access, NUMA, has been the subject of research, and commercial NUMA products are now available, non-uniform memory access. Before proceeding, we should define some terms often found in the NUMA literature. So first we have UMA, uniform memory access. All processors have access to all parts of main memory using loads and stores. The memory access time of a processor to all regions of memory is the same. The access time experienced by different processors are the same. The SMP organization discussed is in section 20.2 and 20.3 is UMA. So the SMP organization discussed in section 20.2 and 20.3 is UMA, just to give you a context. Next, we have NUMA, non-uniform memory access. All processors have access to all parts of main memory using loads and stores. The memory access time of a processor differs depending on which region of main memory is accessed. The last statement is true for all processors. However, for different processors, which memory regions are slower and which are faster differ. Next, we have CC NUMA. So this is cache coherent NUMA. And so a NUMA system in which cache coherence is maintained among the caches of the various processors. A NUMA system without cache coherence is more or less equivalent to a cluster. The commercial products that have received much attention recently are a CC NUMA system, which are quite distinct from both SMP and clusters. Usually, but unfortunately not always, such systems are in fact referred to in the commercial literature as CC NUMA. Okay, with an SMP system, there is a practical limit to the number of processors that can be used. An effective cache scheme reduces the bus traffic between any one processor and main memory. As the number of processors increases, the bus traffic also increases. Also, the bus is used to exchange cache coherent signals. Further adding to the burden, at some point, the bus becomes a performance bottleneck. Performance degradation seems to limit the number of processors in an SMP configuration to somewhere between 16 and 64 processors. For example, Silicon Graphics Power Champion SMP is limited to 64 R10000 processors in a single system. Beyond this, the number of performance degrades substantially. The processor limit in an SMP is one of the driving motivations behind the development of cluster systems. However, with a cluster, each node has its own private main memory. Applications do not see a large global memory. In effect, coherency is maintained in software rather than hardware. Thus, memory gradually affects performance, and to achieve maximum performance, software must be tailored to this environment. One approach to achieve large-scale multiprocessor while maintaining the flavor of SMP is NUMA. The objective with NUMA is to maintain a transparent system-wide memory while performing multiple multiprocessor nodes, each with its own bus or other internal interconnect system. So in figure 2012, it depicts a typical CC NUMA organization. There are multiple independent nodes, each of which is in effect an SMP organization. Thus, each node contains multiple processors. Each has its own L1 and L2 caches, plus main memory. The node is the basic building block of the overall CC NUMA organization. For example, each Silicon Graphics origin node includes two MIPS R10000 processors. Each sequent NUMA Q node includes 4 Pentium 2 processors. The nodes are interconnected by means of some communication facility, which could be a switching mechanism, a ring, or some other networking facility. Each node in a CC NUMA system includes some main memory. From the point of view of the processors, however, there is only a single addressable memory, with each location having a unique system-wide address. When a processor initiates a memory access, if the requested memory location is not in the processor's cache, then the L2 cache initiates a fetch operation. If the desired line in the local portion of the main memory, the line is fetched across the local bus. If the desired line is in a remote portion of the main memory, then an automatic request is sent out to fetch that line across the interconnect network, deliver it to the local bus, and then deliver it to the requesting cache on that bus. All this activity is automatic and transparent to the processor and its cache. In this configuration, cache coherence is a central concept. Although implementations differ as to details in general terms, we can say that each node must maintain some sort of directory that gives it an indication of the location of the various portions of memory and also cache status information. So in terms of the pros and cons for NUMA, the main advantage of CC NUMA systems is that it can deliver effective performance at higher levels of parallelisms than SMP without recurring major software changes. But multiple NUMA nodes, that the bus traffic on an individual node is limited to a demand that the bus can handle. However, if many of the memory accesses are to remote nodes, the performance begins to break down. There is a reason to believe that the performance breakdown can be avoided. First, the use of L1 and L2 caches is designated to minimize all memory accesses, including remote ones. If much of the software has good temporal locality, then the remote memory accesses should not be excessive. Second, if the software has good spatial locality and a virtual memory is used, then the data needed for an application will reside on a limited number of frequently used pages that can be initially loaded into the memory local to the running application. The subsequent designers report that such spatially locality does appear in representative applications. Finally, the virtual memory scheme can be enhanced by including in the operating system a page migration mechanism that will move a virtual memory page to a node that is frequently using it. The Silicon Graphics designers report success with this approach. So we haven't talked much about Silicon Graphics, but it's come up again. So this is an example of a hardware vendor that created its own system that's kind of gone out of I think it may have gone out of business, but don't take my word off the top of my head. I'm just giving you a perspective on it. So what it is. Even if the performance breakdown due to remote access is addressed, there are two other disadvantages for CC NUMA approaches. First, a CC NUMA does not transparently lock like an SMP. Software changes will be required to move an operating system and applications from an SMP to a CC NUMA system. These include page allocation, already mentioned process allocation, and load balancing by the operating system. A second concern is that of availability. This this is a rather complex issue and depends on the exact implementation of a CC NUMA system. So there are some additional references in the text if you wanted to read about that further. Okay, we've come to the end of this lecture, talking about parallel processing. And so hopefully you're now seeing a couple different ways that that can be done. You can have things done at the processor. You can be synchronizing multiprocessors. You can be leveraging something that's an important concept if we have multiple processors and multiple machines, making sure that all of the caching that were used is coherent so that it's clear who's writing to what when and who has the right to do that. And that's where we get into the MESI protocol. We then talked about multi-threading and chip multiprocessing. One of the ways to increase performance is if you have multiple cores in a computer, you can break things up into threads. And so that can be a way that can help performance. We can have clusters, and clusters computers are a way of a lot of standalone computers that are wired together, a few things tweaked in their software so they act effectively as a single machine. And we also talked about non-uniform memory access and talked about some of the pros and cons for approaches like the NUMA and CC NUMA. Okay, well, that's going to end it for this lecture. Thank you very much.